Hi, hello everyone. This is Dr. Chiranjeevi Manike, Professor and Head of Data Science and Cybersecurity Department, MLR Institute of Technology, Hyderabad. As part of data mining video lecture series, in this lecture we are going to discuss K-Medoids. It is a representative object-based technique. So in this we are going to first understand what are the drawbacks of K-means, so that you will understand why they introduced this K-Medoids. The K-means algorithm is sensitive to the outliers. As I discussed, outlier is an extreme value, and that will be discussed in detail in the coming lecture also as part of outlier detection or outlier analysis. So this K-means is a sensitive. It's not robust to the outliers because the objects are far from the majority of the data, and thus when assigned to the cluster, they dramatically distort the mean value of the cluster. So like this inadvertently affect the assignment of other objects to clusters also. So this effect is particularly exacerbated due to the use of a squared error function, that is E here. So where E is the sum of the squared error for all objects in the data set, where P is the point in a space representing a given object, and Ci, small ci, is the centroid of a cluster Ci. Both P and Ci are the multi-dimensional. So consider a 6 points, a 1-dimensional space having values like 1, 2, 3, 8, 9, 10 and 25 respectively. How we would use this K-means, or how the K-means is going to partition, if you apply this K-means algorithm, how it partitions this data set. So here, this is the mean absolute error we are going to use to calculate this, that is to find out the intercluster deviation. So for example, let us say the K value equal to, we are going to apply the K-means algorithm to this data set, and suppose the K equal to 2. Just assume that the K is equal to 2. That means the number of clusters. So in that case, but before, let us just apply some common sense to how we can partition this data set. So now, by just visually observing this data points in this data set, and there are like, we would divide this data set into the two partitions. Like this is one partition and this is another partition. Then we would remove this, or we exclude this 25 because it is completely, it's a big number compared to the rest of the partitions. So then that would be considered as a outlier, so that we could discard it. That is like if you apply the basic common sense. But if you apply the K-means algorithm, how it is going to divide this data set into the partitions. Okay, so how, because let us assume that the 25 is an outlier, then how the presence of outlier is going to affect the K-means clustering, because as I said, it is not a K-means is not a robust to the outliers. So let us understand here. So very simple, we are going to apply this. So here the K-means algorithm, so it would divide the partition, like for example, if it divides, if we select the K is equal to 2, then it would divide into this two partitions. So one partition is going to have the data points 1, 2, 3. So another partition is going to have the data points 8, 9, 10, 25. Okay, so now, and if you calculate the error value by using this equation, now the mean value, that is mu, and because this K-means is mainly depends on the mean value, the object in this partitioning approach would be selected based on the mean values. So here the mu of this is like, there are three numbers, 1 plus 2 plus 3, that is 6 by 3, that is equal to 2, and in this case mu equal to 13. Okay, so then if you plug these values in this equation to find out the intercluster deviation, so then we will calculate the value. Like I will write how we are going to calculate the value, like 1 minus 2 whole square plus, like suppose if you calculate for this cluster both the partitions, like 1 minus 2 whole square, because here the 2 is a mean value for this partition, left side partition, and 2 minus 2 whole square plus 3 minus 2 whole square plus the remaining cluster, that is on the right hand side we have another cluster. So here we have to use this mean 13. So 8 minus 13 whole square plus 9 minus 13 whole square plus 10 minus 13 whole square plus 25 minus 13 whole square. And if you simplify this equation, then we would get the value like 196. So I would write here 196, the value, the error value, because here our objective of this is to minimize this error. We have to minimize this error. So that is, if you divide this into, next let us consider if this cluster, so now another cluster, let us say like 1 2 3 8, and another partition here for the cluster 9 10 25. Okay, so now again we have to calculate the mean value mu, that is for this cluster also. So here 3.5 is the mean for this cluster or the partition, and 14.67, that is the mean of this cluster. So then if you plug these values into this to find out the error, then that means like 1 minus 3.5 whole square plus 2 minus 3.5 whole square plus and so on, plus this is 25 minus 14, let me erase it. So 25 minus 14.67 whole square. So then it's, if you simplify this value, let me write here, that is a 189.67. So which is the minimum value, and this is the minimum value. So in this case, because of the presence of this outlier, this would be selected as the best one. So that's why, so we have to understand that the k-means is not robust to the outliers. So how we can modify this k-means algorithm, that is to diminish such a sensitivity to the outliers. So again we use the K-Medoids method, that is instead of k-means we choose the mean value. We initially select the random cluster heads, then we find out the distance, and once we assign the objects into each cluster, then we'll find out the mean values. So based on that, the remaining iterations would be done. So, but if the presence of outliers, that as we discussed just now, the presence of outliers affect the decision. So instead of selecting the mean based on the selecting the objects based on the mean values, so we are going to select a mode, that is most frequently occurred value, as an object, as a cluster head. Whereas the k-means algorithm, we choose a first initial step, we choose a random cluster head, and the next second and subsequent iterations we select based on the mean of the cluster. we'll find, like, suppose if there are 3 data points and we'll find out the mean, then that would be a cluster head. Then again calculate the distances from each object to the cluster, different cluster heads, and we reassign the objects, and again we'll collect based on the reassignment of the clusters. We calculate the cluster mean of the cluster, and that would be selected or elected as a cluster head. That is the way we in every iteration the clustering would be done based on these k-means. But as we already understood from this previous example, that the k-means algorithm is not robust to the sensitivity to the outliers. So to overcome this, we are going to select this Medoid. So here we are going to calculate the error, that is where here the E is the sum of the absolute error for all the objects P in the data set, and Y is the representative object. So we are going to calculate the distance, and based on that distance we are going to assign. So here the K-Medoid is the basis which groups the n objects into the K clusters by minimizing the absolute error. So how this K-Medoids works, let us try to understand. Here where K is in this case K is can be find the exact median, that is in order of n square time. However, when K is a general positive number, the K-Medoid problem would become an NP-hard problem. So it is a popular realization of the K-Medoids clustering, that is a partitioning around Medoids. It tackles the problem in an iterative, greedy way, like the k-means algorithm. The initial representative objects called as a seeds are chosen arbitrarily, and we consider whether replacing a representative object by a non-representative object would improve the clustering quality, right? Based on that, we are going to select, we are going to replace the cluster head or the representative object by non-representative object if it would improve the cluster quality. Next, all these possible replacements are tried out now. So the iterative process of replacing representative objects by other objects, that will be continued until the quality of the resulting cluster cannot be improved by any replacement. Whereas a k-means, until there is no reassignment, like suppose let us say there are 3 clusters need to be formed, and after the n number of iterations there is no change of assignment of the data objects. That means no object is been reassigned to some other cluster, the same as the previous iteration. That means the assignment of the objects in the clusters is same as the previous one. So then that would be considered as a stopping criteria. We stop at that point. But whereas in the case of this Medoids, the quality measure, that is, so we are going to, like, how we are going to stop, or which criteria we are going to use this. So here we have to replace the representative objects by other objects until the quality of resulting cluster cannot be improved. Like every time we are going to calculate the error. We are going to calculate the error. Based on that, we are going to measure the quality of the clustering. So if there is no change in, or there is no improvement, then we will stop construction. So the quality is measured by a cost function of the average dissimilarity between an object and the representative objects. It's a cluster dissimilarity. Both are different. So let us take one simple example, like how, because we are going to suppose, let us say there are different objects, like object 1, object 2, and so on, object k. There are k objects, representative objects are cluster heads. So we are going to replace an object with a random object. These are representative objects, and we are going to replace one object with a non-representative object. Let us say the non-representative object is a random. This is a random. So we are going to replace this object, that is OJ, where J is in between 1 and K, because there are K representative objects. So how we are going to reassign the objects? Like, so let us say there will be different objects. Each data point would be considered as an object in this case. Like, suppose if you replace a representative object, let us say OJ is a representative object of a cluster, and that would be replaced. If you want to replace that representative object by a non-representative object, that is O random, so then what need to be done? We have to calculate from each object P, and we have to recalculate the distance from each object P to the representative heads. So then suppose, and in this case, suppose the OJ is replaced, that is a representative object OJ is being replaced by the O random. So then we have to calculate the distance from every object. Like, suppose let us say the PI, in this case PI is near close to this data point. Okay, so previously it was been assigned to this object OJ, that is representative object, or the cluster, let us say the cluster. So now, and we are going to replace this OJ by the another non-representative object, that is O random. Then the distance again would be calculated. Let us say the P is another data object which belongs to this, or which is being already assigned to this cluster OJ. Then we have to recalculate the distance. Now if you calculate from this, we can easily find out that, and this data point or object is close to this OI. So then that will be assigned to this OI. So where I is not equal to Z, Y is not equal to Z. So now let us consider another scenario. Like, suppose, and this is the object, suppose the object P is close to the O random, because the OJ is being replaced with the O random. Then the P will be assigned to this new representative object, that is O random. And another case, like, there is no change because it is still close to this OI, and there will be no change in this. So there will be no reassignment would be done here. And another case, like, if suppose the PI is close to this O random, so then it would be assigned to this cluster O random. So let us quickly summarize, like, what is how the replacement would be done, because every iteration we are going to calculate a error value. This is the error value we are going to use, and based on this we are going to measure the quality of the cluster, that is, and the quality is measured by the cost function of the average dissimilarity between object and the representative object of its cluster. So in this case, let me erase this part. I just want to give a quick overview regarding this. Okay, as I said, like, so let us take an example, and let us say this is a cluster, and this is another cluster, and this is another cluster. So let us take three clusters. So for each cluster there will be a representative object. Representative object is nothing but, let us say this is one representative object and this is another representative object. So each cluster is having a representative object. So now let us say, and this representative object is going to be replaced in the next iteration. That means the next representative object would become a cluster head. In that case, that need to be replaced. If that is the case, then on what basis? So how the reassignment of objects. Objects means the remaining all the objects, like those are in this, like suppose these are all the different objects, and there are different objects which have already been assigned to this cluster. There are different other objects which have already been assigned in this cluster. So for every object, we are going to recalculate the distance at the similarities. So based on that, so like suppose, and let us say the new cluster is being, the new representative object is used to replace this old one, let us say this one. So now from every data point, that is, or object, every data point or object, we would calculate the distance. So then based on that, so the similarity, like suppose, let us say this is assigned to this cluster, let us say. Now after replacing this representative object this with another object, if we replace, like let us say, let us just let me complete it as early as possible. The OJ that is already previously assigned, this object P is assigned to this cluster OJ previously. Now we are going to replace this OJ with the O random. So now what need to be done? So we have to, whatever the, let us say, like suppose there are some data points or objects which have already been assigned to this cluster. So now we are going to calculate all the distance, okay, distance from every object to the remaining. So each time a reassignment occurs, difference in absolute error, that is E, is contributed to the cost function. So therefore the cost function calculates the difference in absolute error value if a current representative object is replaced by the non-representative object. So the total cost of swapping is the sum of costs incurred by all non-representative objects. If the total cost is negative, so then the OJ is replaced or swapped with the O random, because the actual absolute error is reduced. If the total cost is positive, that means the current representative object is considered acceptable and nothing is changed in the iteration, because our objective of this equation, that objective function, need to be minimized. So because in this case the negative, the total cost is negative, that means so reduced. So then the swapping would be done, the replacing, that is OJ will be replaced with the O random. But if it is positive, the total cost is positive, that means the current representative object is OJ is considered as acceptable and nothing is changed in this iteration. So now I think we understood what is K means, like the basic definition. As per the basic definition and the examples, we understood the K-means and K-Medoids. So then which method is a more robust, either K-means or the K-Medoids? Let us understand here. The K-Medoids is more robust than the K-means in presence of noise and outliers, as we already discussed, because a medoid is less influenced by outliers or other extreme values than the mean. But whereas a K-means is mainly depends on the mean, which is sensitive to the outliers as well as the noise. However, the complexity of the iteration in the K-Medoids algorithm is order of k n-1 whole square, and for the large values of n and k, such computation becomes very costly, so and much more costlier than the K-means method. In that case, both methods requires, that is K-means would be the better one. Another one is both the methods, K-means and K-Medoids, are required to specify the k, that is the number of clusters. Next one is how we can scale up the K-Medoids method, because we need the data is, whatever the data available is large, so we need to develop the scalable clustering algorithms. So how we can scale up this K-Medoids algorithm? A typical K-Medoids partitioning algorithm, like a PAM, that is partitioning around medoids, works effectively for the small data sets but does not scale well for the large data sets. So to deal with the large data sets, a sampling based method called as a Clara, clustering large applications, can be used. So instead of taking the whole data set into the consideration, Clara uses a random sample of the data set. Like in statistics, we select the sample to estimate the population parameters. So here the PAM partitioning around the Medoids algorithm is then applied to compute the best Medoids from the sample. So ideally, the sample should closely represent the original data set. Otherwise, whatever the clustering would be done, that is invalid. So in many cases, large sample works well if it is created so that each object has equal probability of being selected into the sample. So that is sampling, the effective sampling need to be done. The representative object Medoids chosen will likely to be similar to those that would have been chosen from the whole data set. So Clara builds the clusterings from multiple random samples and returns the best clustering as the output. Here the complexity of computing the Medoids on a random sample would be equal to order of ks square plus k times n minus k, where s is the size of the sample and k is the number of clusters and n is the total number of objects. So Clara can deal with the large data sets than the partitioning around Medoids PAM. So the effectiveness of Clara depends on the sample size. Notice that the PAM searches for the best K-Medoids among the given data set, whereas Clara searches for the best K-Medoids among the selected samples of the data set. So that is a difference we could observe here. And Clara cannot find a good clustering if any of the best sampled Medoids is far from the best K-Medoids. If an object is one of the best K-Medoids but is not selected during sampling, then Clara will never find the best clustering because there is no possibility. Because we are from the population, we are going to select, that means are from the entire data set. This is a data set. We are going to select the sample. What the last point says, if an object is one of the best K-Medoids but is not selected during the sampling, then that means this data has one best object that is to cluster, but that is not being selected while sampling. In that case, the Clara will never find the best clustering. Whereas a partitioning around Medoids, there would be a possibility to select the best Medoid. How might we improve the quality and the scalability of Clara? So we have to recall when searching for better Medoids, PAM examines every object in the data set against every current Medoid, whereas Clara confines the candidate Medoids to only a random sample of the data set. So a randomized algorithm called as a Clarance, that is clustering large applications based upon the randomized search, which presents a trade-off between the cost and the effectiveness of using samples to obtain the clustering. First, it randomly selects the k objects in the data set as the current Medoids. It then randomly selects the current Medoid x and the object y that is not one of the current Medoids. So then now we'll get a question like, can replacing x by y improve the absolute error criteria? If yes, that means the replacement is made. That means Clarence conducts such a randomized search L number of times. So the set of the current Medoids after the L steps is considered as a local optimum. Clarence repeats this randomized process m times and returns the best local optimal as the final result. So thank you for watching this video.